You know, we interact with databases every single day of our lives. You check your bank balance, you scroll through a streaming service to find a movie, or, you search for a flight for your next vacation.
Right, it's just constantly running in the background.
Exactly. And because of how seamless all those interfaces are, it's, well, it's incredibly easy to picture the databases underneath them as just these static filing cabinets.
Yeah, like big metal drawers in a dark room.
Right. We imagine these massive, passive drawers full of manila folders that just sit there waiting for us to pull them open. But when you actually look under the hood, that is not what is happening at all. Databases are living, breathing ecosystems.
They really are.
They change, they react, they enforce strict laws, and in some cases, they actually govern themselves without any human intervention at all. So, welcome to the deep dive. Today, we are taking you on a journey into the life cycle of data itself.
It's a fascinating life cycle, too.
It really is. We're unpacking how information is born, how it connects, how it gets fixed, and how it eventually fades away.
And, to really understand that life cycle, we need a setting. We need a way to ground the highly technical logic of SQL.
Which is the language we use to talk to databases, right?
Exactly, yes. Yeah. We need to ground SQL into something tangible. So we're going to look at a really elegant, real-world scenario. Imagine an old, beautiful postcard of the Museum of Fine Arts, Boston.
Oh, I like that.
Yeah, that is our backdrop today. We aren't looking at generic corporate sales figures or, widget inventories. We are looking at how a digital curator manages a sprawling collection of art.
Using the basic CRU operations, right? Create, read, update, delete.
Spot on. We're talking about managing priceless masterpieces, unknown creators, and the inevitable messy human errors that happen when people try to, categorize history.
I love that setup because before a curator can even think about managing this digital museum, they face a completely blank canvas. Moving from a physical building full of crates and canvases to a structured digital record, that is a massive leap. How do you even translate a physical painting into a line of data in the first place?
Well, you start by defining the boundaries of what you want to know. In database terminology, we are moving from a state of total emptiness to a structured table.
Okay.
You build a primary table with very specific columns designed to hold the metadata of the art. Think of it like creating the ultimate standardized digital plaque for every item.
So deciding exactly what pieces of information matter.
Right. You might have a column for an id, one for the title, one for the accession number.
Wait, accession number? That's like the museum's internal tracking code, right?
Yes, exactly. And then maybe a column for the date the piece was acquired.
And the id column, that's just a unique numerical fingerprint for the database to use internally, right? It's not something a visitor would ever see.
That is spot on. The database needs a way to uniquely identify a record that has absolutely nothing to do with human language.
Because titles can be duplicated.
Exactly. Titles repeat, but an id is an absolute constant.
Yeah.
So once you have those columns set up, you can start bringing the art across the digital threshold.
Okay, let's unpack this. Let's bring a piece in. Take a breathtaking painting called Profusion of Flowers.
Great choice.
Thanks. When this piece enters the digital system, it gets assigned a specific accession number, let's say 56.257, and the record shows it was acquired on April 12th, 1956.
Perfect.
Then you might have an incredible landscape, something like farmers working at dawn. That one has the accession number 11.6152, and it was acquired way back on August 3rd, 1911.
Right. And to get those distinct individual pieces into the database, you use a fundamental command, which is insert into.
Insert into.
It's a very deliberate action. The syntax is essentially insert into, then you name the table you were targeting, list the specific columns you want to fill, and then provide the values that correspond to those columns.
I picture this like a curator meticulously taking a single painting out of a wooden shipping crate, carefully hanging it on the gallery wall, and then sitting down at a vintage typewriter to hammer out its little brass plaque.
That's a really good analogy.
You type out the title, you type out the date, you hit enter. It's a singular, focused action. But if I'm the curator of a major museum, I have to point out a practical flaw here.
Well, what's that?
What if the museum receives a massive estate donation? Like, let's say a wealthy collector passes away and a truck backs up to the loading dock with 500 paintings.
Oh, yeah.
I am definitely not going to sit at my keyboard and type insert into 500 individual times. My fingers would fall off and I'd probably make 100 typos along the way.
No, you definitely wouldn't want to do that. And that scenario exposes the limitation of manual entry perfectly. When you're dealing with a massive influx of data, you need to think about scale.
Right, you need bulk solutions.
Exactly. Instead of typing everything out, databases allow you to import entire spreadsheets at once. One of the most common methods is using a specific import command pointing to a CSV file.
A CSV.
Yeah, CSV is just a simple text file where all the values are separated by commas. It's a very raw form of a spreadsheet.
Okay, so I just tell the database, hey, grab this giant file of 500 paintings and shove them into the collection table.
Almost. But you have to be careful with the nitty-gritty specifics. The command might look something like .import CSV, and then you point it at your file.
Okay.
But there's a crucial flag you usually have to add, which is skip 1.
Let me guess why. If I open a spreadsheet of museum inventory, the very first row doesn't actually contain a painting.
Nope.
The first row is just the column headers. It literally says the words id, title, accession number, and acquired in bold text.
Exactly.
So if I don't tell the database to skip that first line, it's going to think the word title is the name of a new masterpiece.
That is the exact trap. And it highlights something profound about databases. They are brutally literal.
They just do what you say.
They have zero common sense. They do not know the difference between a Ming Dynasty vase and a column header.
Wow.
If you leave off that skip 1 command, the database will dutifully ingest that header row. Suddenly, sitting right there in your beautiful digital gallery next to profusion of flowers, you have a piece of art authored by nobody titled Title with an accession number called accession number.
That is hilarious. The machine just blindly follows the instructions it was given.
Always. You are the human context,
Yeah.
The database is just the engine. Now, if the museum wants to move data around internally rather than importing from an outside file, there's another really powerful bulk command.
Oh, what's that?
It combines 2 different actions. It uses insert into and select from together.
So you're telling it to grab data from one place and immediately drop it into another?
Essentially, yes. If the museum decides to completely restructure its digital archives, maybe they built a brand new optimized table for their Asian art collection, they don't need to retype anything. They can write a command that instantly reads thousands of records from the old messy table and inserts them directly into the new one.
Wow. It's like moving an entire wing of the physical museum overnight with a snap of your fingers.
Yeah, it's incredibly fast.
So our digital gallery is now fully stocked. We've avoided the header row trap. We've bulk imported the donations. But art doesn't exist in a vacuum.
No, it doesn't.
Someone painted these pieces. We have masters like Li Yin, Qin Weiqing, and Zhu Chen. We even have records that just say unidentified artist.
Right.
How does the database manage the artists without just retyping Zhu Chen's name 100 times for every single painting he ever did? I mean, if I spell his name wrong once, my search results are going to be a total mess.
You've just described the core problem that relational databases were built to solve. Data duplication and the errors that come with it.
Okay.
Instead of typing the artist's name into the main collection table over and over, we enforce a structural shift. We build a separate table entirely just for the creators.
Ah, I see.
We call it the artist table. So now we have an artist table, and we have a collection table for the actual art.
And we just need a way for those 2 tables to hold hands, to talk to each other.
We do. And we link them together using something called a foreign key.
A foreign key.
Yeah, it's a mapping relationship. You take the unique id from the artist table, let's call it the artist id, and you insert that specific number into a new column in the collection table.
So instead of writing out Zhu Chen next to his painting Spring Outing, I just look up his ID.
Exactly.
If Zhu Chen is artist number 4 in the artist table, I just put the number 4 next to the painting in the collection table. It's a literal link that just says creator number 4, made collection item number 4.
That is the architecture of a relational database in a nutshell. But the real power comes from what we call foreign key constraints.
Constraints?
Yeah, constraint is a rule that the database actively enforces to maintain reality.
What do you mean by enforcing reality?
Well, if you tell the database that the artisted in the collection table is a foreign key that must match an id in the artist table, the database takes that rule very seriously.
Okay.
You literally cannot assign a painting to an artist that doesn't exist.
Oh.
If a tired curator tries to log a new painting and accidentally types that it was created by artist number 99, but you only have 4 artists registered in your system, the database will throw an error and reject the entry.
That's amazing. It prevents impossible realities from existing in your records.
Exactly.
Wait, so if these tables are practically holding hands, if they are that deeply connected, what happens when we need to sever a tie.
Sever a tie.
Yeah, let's say historians do some digging and we realize Zhu Chen didn't actually paint spring outing.
Okay, a misattribution.
Right. And
Right.
we want to delete his record entirely because he has no other art in our museum.
Mm.
If the database is aggressively enforcing these links, does spring outing just suddenly vanish from the museum's database when I delete its creator?
That separation anxiety is a major design consideration. The database doesn't just guess what you want it to do. You, as the architect, have to define the behavior for when a linked record is deleted.
Oh, so I'm in control of the fallout.
Yes, these are known as on-delete behaviors.
So if I try to delete artist number 4, what are my options for handling that?
The safest, most common options are restrict or no action.
Restrict. Okay.
If you have these rules in place and you try to delete Zhu Chen, the database acts like a brick wall. It throws an error and says, I see that this artist is still fundamentally linked to spring outing. You cannot delete the artist until you deal with the painting first.
I really like that. It acts as a digital failsafe. It forces the curator to be responsible and go update the painting's record before throwing away the artist.
It really does. Another option is set null.
Hmm.
This is a bit more accommodating.
How so?
If you delete Zhu Chen, the database allows the deletion. But it immediately goes over to the collection table, finds spring outing, and changes its creator ID to NL.
Which just means empty, right?
Exactly. Empty or unknown. The artist is removed from the system, but the art remains. It's essentially orphaned until you assign it a new creator.
That makes sense.
You could also use a similar rule called set default, which would automatically assign the orphaned painting to a fallback category, maybe pointing it to the id for that unidentified artist record we mentioned earlier.
Those all sound very reasonable, but, knowing how powerful these commands are, there has to be a nuclear option, right? Like a way to just clear the board.
Oh, there is. It is called Cascade.
Cascade. That sounds ominous.
It can be. If you set your foreign key rule to on-delete Cascade, deleting Zhu Chen triggers a terrifying instantaneous domino effect.
Oh, no.
The moment you confirm the removal of his record, the database sweeps through the entire collection table and automatically wipes out every single piece of art connected to him.
Wow.
The artist falls, and his entire life's work falls with him, permanently deleted in a fraction of a second.
That is genuinely terrifying. I mean, if you hit enter on a cascade deletion by mistake, you might just wipe out half a museum wing without even realizing it.
Which highlights a critical lesson.
Huh.
Managing relationships in a database isn't just about figuring out how things connect. It is largely about anticipating the catastrophic consequences of what happens when those connections are broken.
Right. But even with those strict rules keeping the database structurally intact, you still have the human element.
Always.
Curators get tired, a typo gets made. If a database is this rigid about enforcing reality, how forgiving is it when we need to fix a mistake? Let's talk about rewriting history.
Fixing mistakes brings us to the U in our CRUD operations. Update.
Okay, update.
Let's look at a few beautifully flawed records that need our attention. Take a piece called Imaginative Landscape, accession number 56.496.
Got it.
If you look at its digital plaque, its acquired date is NULL.
So the museum physically possesses the painting, but the digital ledger has total amnesia about when it actually arrived. It's just a void.
A total void. And right beneath it, we have another painting, Peonies and Butterfly. Its acquired date is listed as January 1st, 1906.
Now, wait a minute. While it's certainly possible a painting was acquired on New Year's Day, in historical research, January 1st is usually a massive red flag.
Oh, really?
Yeah, it almost always means a historian knew the year was 1906, but the actual month and day were lost to time. So whoever entered the data just defaulted to the very first day of the year to make the computer accept the format.
That makes total sense.
I'll say.
And that is incredibly common with historical data sets. So let's say a researcher digs into the archives and finds the exact original receipt for Imaginative Landscape.
Awesome.
We need a digital eraser and a pen to fix that NLL value. The tool for that is the utate command.
Let's slow down and translate the code for that. How do I actually tell the database to fix it?
It's basically a three-step instruction. The syntax is update table set column equals value where condition.
Okay, 3 steps.
Step 1. You use update to target the specific table, in our case, the collection table. Step 2, you use set to declare the specific column and the exact new value you want to inject.
And step 3?
Step 3, which is arguably the most critical part, use a where clause to filter exactly which record should receive this new data.
Ah, okay. Here's where the danger really kicks in. I have actually made this mistake myself in smaller spreadsheet macros.
Oh, have you?
Yes. That where clause is doing all the heavy lifting to contain the blast radius of your command. If you get distracted and hit enter before typing the where clause,
It's bad.
it's like handing a bucket of paint to the museum staff and saying, please paint the frame gold, but completely forgetting to point at the painting you wanted framed.
The staff would just paint every single frame they could find.
Exactly. Suddenly, every single piece in the entire museum, from the sweeping canvas of profusion of flowers to a tiny little statuette in the basement, gets a gold frame.
It's a disaster.
If you just type update collection set acquired equals 1956-0412 and hit enter without that filter, congratulations, you've just rewritten the history of the entire museum. Every single painting now shows that it was acquired on that exact day in 1956. You've corrupted the entire data set in a millisecond.
It's a devastatingly easy mistake to make, and there is no simple undo button in SQL.
No undo button at all.
Nope. This is why database administration requires this incredible mix of immense power and immense caution. These systems execute the logic you provide flawlessly and mercilessly.
Mercilessly, I like that word for it.
To avoid the gold frame scenario, your where clause needs to be airtight. You don't update based on a title, because there might be two paintings called Imaginative Landscape.
Right.
You target that unique fingerprint we established at the very beginning. You write where id equals 4.
Using the id.
It is the only way to be cryptographically certain you are modifying one and only one piece of history.
Okay, so we can carefully insert art, we can link it to artists without creating chaos, and we can fix our typos without corrupting the whole museum.
Yes, we're in good shape.
But what if a piece of art leaves the museum entirely? Like maybe it was legally repatriated to its country of origin, or I don't know, maybe it was tragically destroyed in a fire. How does a database handle letting go?
This moves us into a fascinating territory: the practical and psychological differences between true deletion and archiving.
Archiving, okay.
Let's take a couple of items we might need to remove from our active view. Say, an architectural fragment called a tile lunette, or perhaps a small statuette of a shrew.
If the shrew is destroyed, my first instinct is just to delete the row. I mean, I don't want it showing up in my inventory searches if it doesn't physically exist anymore.
And you could use the literal delete command for that. The syntax is delete from table where condition. It targets the specific row, and it permanently vaporizes the data from the hard drive. It is gone forever.
But surely a museum wouldn't want to completely erase the fact that they once owned a priceless artifact.
Right.
Even if the piece is gone, the historical record of its existence, when it was acquired and who created it, is still incredibly valuable data. Is there a middle ground between keeping it active and destroying the record entirely?
There is a brilliant structural trick for this, called a soft deletion.
Soft deletion, how does that work?
Instead of destroying the data, we alter the architecture of the table itself to hide the record in plain sight. You literally add a brand new column to your collection table, simply titled deleted.
Just a column named deleted.
Exactly. And this column operates on a simple binary system, zeros and ones. A war row means the record is not deleted. A win row means it is considered deleted.
Oh, that is so elegant. So if I look at the database row for the painting farmers working at dawn, way over at the end of its record, there's just a 0 sitting in the deleted column.
Yes.
So it's active. It's visible to the public.
Correct. But if we need to remove it from the gallery floor, we don't actually use the destructive delete command at all. We rely on the update command we just mastered.
Ah, I see where this is going.
We update the table and carefully change that 0 to a 1 for that specific painting.
It's the digital equivalent of taking a painting down from the public gallery walls and moving it down into the underground archives. You aren't throwing the canvas into an incinerator. The database still remembers the art. It still has the accession number, the original acquisition date, the link to the artist.
Also there.
But by just flipping that single digit from a 0 to a 1, it's now hidden. The museum's website or the search terminal in the lobby is just programmed with a simple filter that says, only show results where the deleted column equals 0.
It perfectly preserves historical integrity. The record remains intact for the historians, but it stops cluttering up the active, public-facing inventory.
This idea of a secret underlying memory, this hidden ledger of things that have happened but aren't currently visible, it leads us beautifully into our final concept. If the database is smart enough to hide things with a soft deletion, can it also watch things? Like, can it monitor itself?
It can. And it does this through incredibly powerful tools called SQL triggers.
Triggers.
This is where we officially move from viewing the database as a passive storage unit to seeing it as an active, self-governing entity. Imagine you have a completely separate table called transactions.
Okay, a transactions table.
Its only job is to track the movement of art. It holds records like spring outing sold or peonies and butterfly bought.
Now, I could have a human curator manually type those entries into the transactions table every single time they buy or sell a painting.
You could.
But we already established that humans are flawed. They get tired, they forget, they make typos. How do we make the database do the administrative work for us?
You programmer reflex. A trigger is essentially digital tripwire, or like an automated museum accountant that never sleeps.
That sounds incredibly useful.
It is. You write a script that tells the database how to react to a specific event. The syntax starts with create trigger, and you give the trigger a name.
Okay.
Then you define the temporal condition. Does this tripwire go off before an event happens or after an event happens?
And what kind of events are we talking about here?
The CRUD operations themselves. You can attach a trigger to an insert, an update, or a delete command on a specific table.
Wow.
So you are telling the database to monitor its own actions. Then you add a crucial phrase, which is for each row.
For each row, what does that do?
This guarantees the trigger is granular. It doesn't just look at a bulk action as a single event. It pays attention to every single individual item being altered.
Okay, that makes sense.
Finally, you wrap the instructions in a begin and end block, which contains the exact code the database should execute when the tripwire is crossed.
Okay, let me try to put all of that together into plain English.
Let's hear it.
I could write a trigger that basically says, listen up, database. Every single time a human uses the delete command on the art collection table, I want you to pause.
Right.
Before you actually vaporize that row, I want you to automatically grab the title of that painting, attach the word sold to it, and insert that note over into the transactions table.
That is a perfect translation. The moment a curator attempts to delete spring outing, the database intercepts the action.
It jumps in front of it.
Exactly. It forces a paper trail to be written before the art is allowed to vanish. You no longer have to trust the human to remember to log the transaction, because the database enforces its own audit logging at the foundational architectural level.
It manages itself.
It really does.
So what does this all mean for you listening? I think it radically shifts our entire perception of what these systems are. They aren't dumb metal filing cabinets.
Not at all.
They are dynamic, reacting ecosystems. They enforce reality so we don't create impossible historical records. They give us tools to surgically fix our mistakes. And with triggers, they keep an unalterable, automated diary of everything we do to them.
It is a profound shift in perspective. If we step back and synthesize the journey of our digital museum today, we started with carefully inserting a single floral painting into a blank system.
Right.
We explored how relational tables use foreign keys to map an artist's life's work without duplicating data. We saw the raw power of precise updates to fix historical anomalies.
The digital eraser.
Yes. And finally, we explored how the database preserves its own history, both through the clever architecture of soft deletions and the vigilant automation of self-executing triggers.
It really makes you look at the digital world differently. I mean, every time you interact with an app or a website, there is an entire unseen layer of logic actively organizing reality.
It's everywhere.
Which leaves me with a final, lingering thought for you to ponder. We just explored how modern, sophisticated databases use soft deletions to merely hide records by quietly flipping a 0 to a 1. And we know they use automated triggers to silently log every single attempt to remove information. If the immense systems that run our financial institutions, our social networks, and our histories are fundamentally engineered to never truly forget a single transaction,
Yeah.
does deleting something in the digital age even exist anymore, or are we all just politely asking the database to close its eyes?